Hello. Well, at this point, we're going to do the questions at the back of Chapter 10. So, let's see. I'm looking at page 349, and these are the review questions. 349, these are the review questions. We'll go through these quickly. Let's see, I got my pen and everything. So, okay, let's see. Number 1. Whoops. F equal ma. I have that just for focusing. All right. Number 1. A spring and mass spring combination system is displaced from equilibrium by 5 centimeters, and its period of motion is determined to be 3 seconds. What will be the period if it is displaced from equilibrium 15 centimeters? Okay, well, actually, the period of a spring is actually independent of the amplitude. That is, if you pull the spring down a little bit and then let it go, it vibrates. Then you pull it down even further and let it go. It oscillates, simple harmonic motion. It oscillates back and forth. The period is the same, no matter how far you pull it down. Now, let me say, the book doesn't talk about this, or maybe it does, I'm not sure, but upon essentially the first approximation, it doesn't. According to the physics we learned in this book, the period doesn't matter no matter what the amplitude is. That's the correct answer, and that's the book answer. Now, in actuality, technically, is that exactly true? Not exactly, because there are errors that are introduced to that when you make the amplitude larger and larger, and the spring maybe goes into a nonlinear region. But for the purposes of this book and for the kind of the simple physics we're doing, the answer is that the period stays the same, irregardless of what the amplitude is. What is the definition of restoring force? Okay, again, I'm going to get, I'm going to get my spring here, which is really a slinky. Everyone loves a slinky, but I'm going to use this for purposes of a spring. If we let the spring go, and suppose there's a mass dangling from here, and it's hanging at an equilibrium position, again, the restoring force is, if the displacement is down, the restoring force acts in the opposite direction. If we push the spring up, the displacement is up, but the restoring force acts down, so the restoring force always acts in the direction to equalize the spring back to the equilibrium position. So the restoring force is the force of the spring, and of course we know the formula is restoring force is equal to negative kx. The k is the spring constant, the x is the displacement, and the negative sign simply indicates that the force is opposite the direction of the displacement. If the displacement goes down, the restoring force tries to push it back up. If the displacement is up, the restoring force tries to push the spring back down. Okay. Okay, number 3. A mass spring system is displaced from equilibrium by 34.1 centimeters. What is its amplitude? 34.1 centimeters. That would be its amplitude. What condition, number 4, what condition must be met in order for the system to exhibit simple harmonic motion? Simple harmonic motion is the oscillatory motion, kind of a sinusoidal wave motion that we get from either a pendulum or a spring when it's in oscillation. And what are these? What are the basic conditions? The basic condition is that essentially that it obeys the restoring force obeys essentially Hooke's law, F equal minus kx, or we say that the restoring force is linearly proportional to the displacement, and it's opposite to the displacement. That's what the negative sign is. So essentially, the Hooke's law, force equal negative kx, or the restoring force is proportional to the displacement, negatively proportional to the displacement. That brings about simple harmonic motion. If the restoring force was not linearly dependent, but say it was, related to the displacement squared, or maybe the square root of the displacement, would we get simple harmonic motion? No. The system would still oscillate. It would certainly oscillate, but would it be simple harmonic motion as described by a perfect sine wave? No, it would not. It would oscillate, and it would be some kind of jerky. It would still oscillate, but it would not be a simple harmonic motion. We might call that a complex harmonic motion. Okay. Number 5. In a mass spring system, where does the system reach its maximum speed? It reaches, let's first see, when it reaches the slowest, like think on a pendulum, when it reaches the slowest speed, it's when it's far out, when the pendulum is when the pendulum's out on either side, it actually goes to 0. When it's right in the center, it reaches its maximum speed. Same thing with the spring. It would reach its maximum speed when the mass is going through the equilibrium position. Where in 6, when is it subject to the greatest force? It's subject to the greatest force exactly when the velocity goes 0, when it's on its outer extremities. Like when the spring is stretched or compressed to the maximum displacement, that's when it will be having its maximum restoring force. Where does it reach its max? 7, when does the system reach its maximum potential energy? It reaches its maximum potential energy when it has its maximum potential force. Because in this case, the force, think of the potential, the force is what gives it its potential energy, okay? It's kind of like a stored up battery. Number 8, a heavy box is dropped on a spring, and the maximum compression of the spring is measured before the spring pushes the box back up. If the box is dropped from a greater height, what will happen to the maximum compression of the spring? Well, it will compress it further, right? Right? That's pretty right. Yeah, that's makes sense. Number 9. Which of the following situations results in a simple harmonic motion? You have a pendulum. A is when it's in a small angle away from the equilibrium. B is when it's a large angle. Okay. Well, the book says, and it's exactly right, that when you have a pendulum, simple harmonic motion is valid when you have a relatively small angle. Okay. When you have a large angle, it's not a simple harmonic motion anymore. It's a little bit more complex. And actually, the lab, let's see, there's an extra credit question, I believe, in the lab that actually talks about that. Okay, number 10. If a pendulum's period is measured on Earth, and then the same pendulum is measured on the Moon, where will you find the period to be the longest? Okay, well, let's see. What's the formula for the pendulum? This is the period for a pendulum. Okay, where the pendulum swings back and forth, and this is L. This distance is L. Okay. Now, we have two situations. Let's see. We have the situation say period for the moon is when the gravity is, the length is the same, but the gravity is, for the moon. And the period for the Earth is the exactly same formula, but we have to plug in the gravitational attraction for the Earth. Now we know that this number is smaller than the Earth. So what would that happen? If this number comes out to be whatever number it is, this number, and this number is smaller, okay, if we divide by a smaller number here, if this number is smaller, okay, than the gravity for the Earth, that will force this ratio to be larger, which means this will be larger. So actually that means that the period for the moon will be larger than the Earth. Will be larger than T Earth. Okay. So if the period's larger, it takes longer. Okay. So that means that when you're on the moon, if say you have a period on the Earth that's like 2 seconds. It's a long pendulum, takes 2 seconds to get from one end back to the other, 2 seconds. If you measure it on the moon, it would be longer. Maybe it would be more like 2.5 seconds, or maybe 3 seconds. Depends on what the ratio of this is. I'm not quite sure. So it would take a longer period of time for the pendulum to swing on the moon, because the gravity's smaller, which forces this ratio larger, makes the period longer. Okay. Let's go to page 350 and go over the problems. Let's see here. Okay, number 1. A hanging scale uses the fact that the length of a spring stretched is proportional to the weight of an object suspended from it. This is page 350, number 1. If a 10-Newton bag of vegetables causes a spring to stretch 5.6 centimeters, what is the spring constant? Well, that's just a simple thing of, here's the, say this is the equilibrium position. You put a mass on here, and this position right here slides down to here, and that becomes, this displacement is 5.6 centimeters, and you have the mass here is a 10 Newton mass. So the spring constant, so we know Hooke's law is F equal minus kx. Okay, so now remember, the F here is really remember F here is the restoring force of the spring. You remember we did this before in the lecture. If we just draw a simple force diagram of this mass, we have the weight, which is 10 newtons acting down, and that's balanced by, because this thing is not moving, so it's in static condition, so it has to be balanced by the restoring force, restoring force of the spring, since the sum of the forces is 0. So the restoring force acts up, and the weight acts down, and the sum of those is 0. So obviously the restoring force is equal to the weight. And so what we can say is that the weight is actually equal to the restoring force. They're equal actually in opposite signs. So I'm going to go ahead and take away the minus sign here. Actually, these two are numerically equal. There's a minus sign in here. So I'm going to go ahead and just take the minus sign out. So basically we have that the weight is equal to K times X, or really delta X. So the spring constant is simply the weight divided by delta X, and we have, let's see, the weight is 10 newtons. And if I convert this to meters, 0.056 meters, I get 0.056 meters. And I divide, and I simply get 10 divided by 0.056, and I get, oops, I get 178, but I'm going to round it up to two significant figures, so I would get 180 Newton per meter. And that's spring, so the spring constant is in terms of newtons per meter. That's 180 newtons per meter. Again, or really I could say 1.8 times 10 to the second to get across that there's really only two significant figures here. Okay, number 2. That's number 1. Okay, number 2. A dart gun consists of a horizontal spring with a spring constant of 52 newtons per meter that is compressed 4.3 centimeter when the gun is locked and loaded. What is the initial acceleration of a 75-gram dart when the gun is fired? Now that's an excellent question. Okay, do you understand? Basically, you have a spring-loaded gun, and I'm going to kind of draw it like this. And there's a spring here that's compressed. Normally, it's the let's say the equilibrium position is here, but it's compressed here, so it's compressed a certain amount. And it gives you, let's see, it gives you what the spring constant is, 52 Newton per meter. That's the spring constant. And it's compressed 4.3 centimeters. Let's see, can you see that? Yeah, I think so. Yeah, you can see the 4.3 centimeters. And there's a mass here right in front of it. And the mass here is 75 grams. And when you fire the thing, it's going to shoot out here. The question is, what is the initial acceleration? The initial acceleration is what? Well, that's a very good question. Okay, now remember, when this thing fires off, at this point, okay, there's a release mechanism that totally releases the restoring force. The spring is trying to push this mass back to the equilibrium position, right? Okay, and it does it with a certain force. So that force is the restoring force. I'm going to ignore the minus sign right now, but here it is. That's the restoring force. Now, are there any other forces acting on the mass? Well, there's gravity, but right now let's ignore that because this thing's moving horizontally. Okay, so what we would say is that the sum of the forces, the sum of the forces is only one. There's only one force, and that's the restoring force of the spring, restoring force. That's equal to K delta X. All right, we know that that's the spring, but all of this is equal to mass times acceleration. Remember, F equal ma. And in this case, the only force we have is the restoring force of the spring. Okay, so this force, the restoring force of the spring, which is equal to this, will accelerate the mass with a certain acceleration right here. So we can solve for the acceleration. The acceleration is equal to k times delta x divided by the mass. Okay? Hopefully this makes sense. We're kind of incorporating Newton's second law here. So the spring, I'm going to kind of work right to left in this case. Spring constant is 52 Newton per meter. Delta x is 4.3 centimeters, which is 0.043 meters. Doing that conversion in your head, 0.043 meters, divided by the mass, which is 75 grams, which is 0.075 kilograms, divided by 1,000, 0.075 kilograms. Okay, so let's make sure these units are right. We can, well, we can divide this out, but let's look at the units. A Newton is a kilogram. Well, let me see. First of all, these meters cancel out. These meters cancel out. So we're left with Newton per kilogram. And a Newton is a kilogram per meter second squared divided by kilograms. Obviously, kilograms cancel out. Giving us units of meters per second squared. So the units work out to acceleration units, which is good. They should. Okay, so all of this is equal to, let's see, the acceleration is equal to 52 times 0.043 divided by 0.075. And I get, I'll round off at two significant figures, I get 30 meters per second squared. Okay? And let's see, 52 times 0.043 divided by 0.075. And I'm rounding off to two significant figures. I think the book gets the answer 29. It's probably because of a round-off error. They probably, I suspect, because the book often does this, the book got the number 29. Probably what happened is they broke it up into two steps, and I bet he rounded it off at the first step, whereas I just did it all in one fell swoop, which I think is more appropriate. And so I would only round off at the very end. That's why I get something, a number a little bit different. This is a round-off problem. Anyway, I hope this is clear. This is a very good problem because we're incorporating the spring constant and the restoring force idea with F equal ma. That restoring force causes a mass to accelerate. So it's a very good problem. This is exactly, by the way, how you would design little toy guns and even big toy guns with big springs and things like that. So. Okay, number three. Number three, a 50-gram puppet bounces on the end of a loose spring. What is the period of its motion? Okay, this is simply, I'm not going to do this. Well, I'm going to just talk about it. Basically, this is, you're just simply using the equation, using this equation, and you have the spring and the mass, and you pull it down, and it oscillates back and forth. And now remember, the period, if you start here, goes to here, and it goes back. So a period would be one complete motion from here to here, back to here. So that would be the period. You simply plug the numbers into here. Now remember, the important thing is the mass is given in terms of 50.0 grams. That needs to be converted into kilograms. Okay, because the spring constant is given in newtons per meter. So always use a metric, always use the MKS, meters, kilograms, second. So I'm not going to work it out, but you simply plug these numbers in, and you come up with the period. The answer should be 1.1 seconds. Okay. Now, number 4 is very similar. I'm going to also do number 4. Number 4 is you have a 0.4 kilogram mass attached to a spring, and you set it into motion, and you measure the period, 1.7 seconds. In this one, what you do is you measure the period. The period is 1.7 seconds. Let's see, and you know what the mass is, 0.4 kilograms. And the question is, what is the spring constant? And this is a very good way of measuring what a spring constant is, just by measuring the oscillation. It's, what is this mass? Well, how would you figure that out? Well, you simply arrange your formula here. If I square both sides here, I would get t squared equals 4 pi squared times m over k. M over k, and if I solve for k, I would get k equals 4 pi squared m divided by t squared. Is that right? Yes. Yes, that's right. So you simply plug in your mass, you plug in your t squared, and the constant, and I'm not going to work it out, but the constant should come out to 5.5 Newton per meter squared. Okay, that's what it should come out to, and I'll let you work out the details. Okay, and similarly, number 5 is something quite similar. In number 5, the exact same arrangement. You know what the period is, 1.1 seconds. You know what the spring constant is, 30 Newton per meter. And the question is, what is the mass? Okay, well, in this case, so use the exact, you square both sides, you solve for the mass here, so the mass would simply be t squared times k divided by 4 pi squared. That's equal to the mass. So you simply plug all these numbers, seconds, newtons per meter, and you solve for the mass. And I'm not going to do it, but if you plug those numbers in, you should get, according to the book, 0.92 kilograms. Okay? Okay. So, all right, that's a real quick rendition of 3, 4, 5. They all use the same formula, which is the period formula for a spring system. Okay. Let's see, 6. Whoops. Okay, how much work does it take to compress a spring? It gives you a certain distance, and basically you have a spring, and you want, here's a spring, and you want to compress it a certain distance. Okay. The spring constant is 78.1 Newton per meter, and the distance you want to compress it, this distance delta x, they tell you is 51.1 centimeters. Okay, well, do you remember the formula? The potential energy to compress a spring is 1/2 K delta X squared. Okay, 1/2 K delta X squared. That is the potential, and that's back on page 335. And during the lecture, we actually derived that. Do you remember? You had to use a little calculus. We derived it, but that is the equation. So we simply plug into this. In this case, so it's 1/2 times 78.1 newtons per meter times, I'm going to convert that to meters, 0.511 meters. Notice that the meters cancel out. And, whoops, I have to square it. I forgot about that. Only one of them cancels out, but one does not. So we're left with a Newton meter. Remember what a Newton meter is? That's the same thing as a joule. Okay, so we get 0.511 square that times 78.1 times 1/2, and I get 10.2, and joules, rounded off to 3 significant figures. Okay, so it takes a certain amount of energy to compress a spring a certain distance, and that would, without that